filtering searches. We discussed the different filter options that are available to us by IPA, such as filtering for biofluids, such as uh, what's called molecules that are found in the blood, in the plasma, etc. The type of publication date ranges we want to select for, that being newer studies versus older studies. The specific cell lines we want to select for, such as macrophages, etc. Macrophages, nervous system, etc. There's quite a few options that you can select for. We also discussed the shortest paths plus one and shortest paths. So shortest paths is when using Path Explorer, it is the minimal number of nodes that can connect one node to the other. That is what shortest paths was, and shortest paths plus one is one additional node to the shortest paths. So say, for example, the shortest paths has two intermediary nodes that connect one node to the other. The shortest path plus one will be three. So it can be, it can also be, for example, shortest path might be one node between one molecule and another, one intermediary node between one molecule and another. And shortest path plus one would just be two intermediary nodes between one molecule and another. We also discussed the different layout options that IPA asks for us, such as hierarchical, subcellular, radial, and we also discussed how to export our data as well. And exporting our data is important, especially if you want to publish our data. It is the official method to publish our data by exporting our data, our pathways. For today's session, we'll be discussing the molecule activity predictor, the keep function, and the trim function. And before we begin, I'd just like to remind you as well that there will be a question and answer session. And after the question and answer session, there will be a quiz. So please do not leave after the question and answer session, as there will be a quiz. And the points from the quiz will, if you come in first, second, third, fourth, or fifth, there will be points that go towards the final quiz, which will be on our final session on the 31st of August. And there is a monetary prize for that final quiz. So if you come in first, second, third, fourth, fifth in any of the quiz, in today's quiz, or any of our prior quizzes as well, you will have points depending on what place you came in first, second, third, to the final quiz. And we will be publishing the results from the quizzes on the Google Drive, so you can have a look at that, and we'll be going over who has how many points going into the next session as well. Okay. So before we get into today's topic, we'll just review the task from the last class. So last class, I asked you to connect calcium and potassium to osteolysis, osteolysis being the breakdown of bone. And I wanted you to select it as a connective tissue disorder. And I also wanted you to specify for publications between January 1980 to December 2023, and also select for the relationship types of activation, correlation, expression, and transcription. So if you would have gone ahead and done that, you would have gone something that looks like this. So calcium and potassium over here, connected to osteolysis. I had already gone ahead and rearranged the nodes, so you are able to move around the nodes. So I moved around the nodes to make it look somewhat more visually appealing, and you should have gone a pathway that looks something like this. Okay. I also asked you then to use the layout options available to you to make it into a circular layout, this pathway. So if you would have rearranged it into a circular layout, you would have gone something that looks like this. Okay. I also asked you to connect ethanol and morphine to pentraxin 3. And I wanted you to specify for macrophages and also the relationship types of activation, causation, correlation, expression, and transcription. So these relationship types, and specifically in macrophages. So the shortest paths would have produced something that looks like this. So morphine has a connection with pentraxin 3. The intermediary nodes are TLR2 and TLR4. Ethanol has no connection with pentraxin 3. I also ask you then to add the shortest paths plus one. So if you would have gone ahead and added the shortest paths plus one, you would have gone something that looks like this. So with the shortest paths plus one, ethanol does indeed have a connection with pentraxin 3, but the shortest paths did not have any connection with pentraxin 3. Okay. And like I discussed before, today we will be going over the molecule activity predictor, the trim, and the keep functions. Before we delve into these specific functions, we'll just do a quick review of the previous session, the topics that we reviewed in the previous session, just as a quick refresher. Just so like anyone that may have missed the last session as well, just a quick refresher of that as well. Okay. So last session we discussed how to filter our searches. So the different filter options that we discussed were data sources. So the data sources include, the Ingenuity data, so IPA's own data that they have accumulated from different publications, and it also consists of third-party sources as well. So third-party sources such as the mouse genome database, the mRNA, microRNA interactions, etc. There's quite a few third-party sources that are available that IP has included into their system. You can also filter for the confidence level, the species, that being humans, rats, mice, like different clinical trials, clinical trials being human studies, animal trials, rats, mice, right? Also able to select for tissue cells, cell lines, mutations, relationship types, etc., right? Publication date range as well. And we discussed that the significance of filtering is one that oftentimes it is a component of your research. So with systematic reviews and meta-analysis, you often have certain inclusion and exclusion criteria. So you don't accept all of the data, right? You have to specify your information. You might want the most recent literature. So you'd want to specify for the publication date range to select for perhaps the most recent literature within the last 10 years, as an example, right? So that's one of the uses with the filtering options that you have available, that you can filter your searches for the needs of your research, right? Another benefit is that oftentimes prior to filtering, you may have a lot of different relationships, a lot of different connections, and there can be hundreds of thousands of different relationships. And upon filtering, it can drastically reduce that number, right? So it becomes a lot more easy to follow through after filtering, right? And another benefit that we discussed was that oftentimes the effect after filtering is different prior to filtering. So, for example, if we take a molecule, right, that prior to filtering, that molecule would have been shown to be inhibited in our relationship, right? But after filtering, it might show that that molecule is now activated based off our specific criteria for filtering our data, right? Say, for example, we specified for human studies, right, clinical trials, and we specified for the most recent literature within the last 10 years, right? After filtering for those specifications, we find that, okay, this molecule is actually activated. Prior to filtering, it might have been inhibited, right? So that's another thing to keep in mind, that the effects that you see are often different after you filter your information. So that's another benefit. And the little example that we looked at for how it might look prior to filtering versus after filtering, we looked at morphine. So morphine prior to filtering, I used the grow feature for morphine. I grew morphine, and if you remember, the grow feature was that you for a specific molecule, you can see all the related relationships to that molecule, right? So in this case, we grew morphine and we applied no filters, and we found that there were 307 relationships to morphine. Okay. And after filtering for macrophages and publications between 2000 and 2024, we found that there were 23 relationships. So in this case, it is a quite drastic reduction in the number of relationships that you have. I also might want to keep this keep this in note as well, that it's not always that the number of relationships that it shows after filtering will be reduced. In most cases, it will. I have, in my personal experience, found that after filtering, there is an increase in the number of relationships, depending on what specifications you make. And that has to do with the algorithm that IPA uses. I, in fact, did speak with IPA, with Kaijin about this, right? But just keep in mind that in most cases, however, after you filter, the number of relationships do tend to decrease. Okay. We also discussed the different layout options as well that that we can organize our data into. These being organic, circular, radial, hierarchical, and subcellular. In order to find the different layout options, there's this button right here, which is next to the view button right here, right? There's this button, this specific button you click on. It takes you to this specific panel, right? Where you can select organic, circular, radial, hierarchical, subcellular layout types. The organic layout type looks something like this. The circular layout looks like this. You can see all the individual relationships as all the different nodes are on the periphery and the lines are in the center. The radial layout looks like this. The central node that you're looking at is in the center and all the periphery nodes are on the outside. The subcellular layout looks like this. The subcellular layout basically organizes the different molecules based off their subcellular location. So if, for example, a molecule is found in the extracellular space, it will be over here, and it's also labeled extracellular space right here. If it's found within the plasma membrane, it will be located over here, right? If it's found within the cytoplasm, it will be found here. Found in the nucleus is found here, right? So it's just subcategorizes based off the subcellular location of the different molecules. Okay, and you can also organize it in a hierarchical layout. This is the same pathway as here. However, this layout is very clearly quite bad to keep it to say frankly. The different nodes are quite far apart, and it's not quite practical, right? So I just included this because this is the layout that IPA provided for us, and I just decided to include it also because just to let you know that you don't have to include the layout options that IPA provides for you. You're able to move these individual nodes as well, and you can make it look more visually appealing as you see fit, right? You don't have to use it, as exactly as IPA provides you. You're able to move things around, fit your specific needs as well, right? And this is an example of a hierarchical layout where the nodes are not very spread apart. So on one hand, it may provide you something like this, but the layout option can also look something like this. And both of them are the hierarchical layout. So, just to your own needs, you can rearrange the nodes as well. Okay. We also discussed the shortest paths and shortest paths plus one. Like I mentioned prior, the shortest paths is the least number of nodes that can connect two molecules slash nodes to one another. And this is specifically in the Path Explorer function. So the Path Explorer, you basically see all the relationships between one node and another node, right? So the example that we looked in our last session was ketamine and morphine connected to NMDA. NMDA being a neurotransmitter, ketamine being a anesthetic, morphine being an opioid analgesic. So both of these were set as set A, and NMDA was set as set B. And we used the Path Explorer function, and we connected both of these together, right? Going from ketamine and morphine to NMDA. And in the shortest paths, we found that there were two intermediary nodes, okay? So that was the shortest paths, right? There are two intermediate nodes. This is the least number of nodes, like going from ketamine, then over here there is BDNF, then NMDA receptor to NMDA, right? That's two in between, right? So that is the least number that you connect for these. The shortest path plus one is basically just one additional, right? So if in the shortest path there's two nodes, in the shortest path plus one, there'll be three nodes. So it's just an additional node on top that you can connect, set A to set B with. Okay, and it doesn't have to be two nodes for shortest paths plus one. There can also just be one node. So like for example, like ketamine, after ketamine, it could have been NMDA receptor to NMDA, right? And shortest path plus one could have been two nodes in between. So it's not necessary that shortest path plus one will always be two intermediary nodes. It could be one intermediary node. It could be two intermediary nodes. It could be three intermediary nodes, right? It can be any number, but just know that shortest path plus one will always just be one on top of that. So if shortest paths is two, shortest paths plus one will be three. If shortest paths is three intermediary nodes, shortest paths plus one will be four intermediary nodes. So that's just something to keep in mind. And basically, like the example that we looked at was connecting morphine and ketamine to IL-1. So in the shortest paths, we found that there was this one relationship, and that was just between morphine and IL-1. There was no relationship with ketamine and IL-1. And after adding the shortest path plus one, we found that there was an additional 10 relationships as well. So ketamine does have an interaction with IL-1 if we're including the shortest paths plus one. However, there was none if you just included the shortest paths. So just something to keep in mind that in your own research, you should also check the shortest paths plus one. Just don't forget to not check it, right? And yeah, oftentimes you may not find something in the shortest paths, right? But you may find an interaction in the shortest paths plus one, right? So we'll get on to the topic for today. So the first thing that we're going to be discussing is the molecule activity predictor. So basically, what the molecule activity predictor is, you're basically using IPA's own ingenuity data. So that being like the own IPA's own sources of data, their ingenuity data, and also the third-party sources, right? So all of the publication data that IPA has, and using that publication data, what you can do in your pathway is that, okay, if say hypothetically, for a certain molecule, say for example with morphine as an example, right? Say morphine, in this pathway, you were to increase the quantities of morphine, increase the measurements of morphine, right? Or decrease the measurements of morphine, what effect will that have on the pathway? That's basically what you're able to do with molecule activity predictor. That you're and it utilizes the ingenuity data, the data that IPA has from its publications to make those predictions, right? So the red symbol, right? So you're able to make, for example, morphine. You're able to increase the measurements. Once you increase the measurements, it will turn a red color like this, right? And that means that you have increasing measurements of morphine and it will appear red. If you're decreasing the measurements of a certain molecule, it turns green like this, okay? So increased measurements is red, decreased measurements is green, right? And for the downstream molecules, it can basically predict, okay, so after increasing the measurements or decreasing the measurements, what will be the effects on activation or inhibition of the downstream molecules, right? Downstream or upstream molecules. So if it's predicted activation, right? So if the downstream or upstream molecules will be activated, it will be an orange color like this. And if it's predicted inhibition, then the downstream or upstream molecules will be blue. And basically, the degree of how strongly how darker or lighter it is of a orange or blue shade will it's called denote the level of confidence in the predicted activation or inhibition based off of the publication data that's available, right? So based off that publication data, it tells you, okay, is this a strong predicted activation or is it a weak predicted activation, right? So orange predicted activation, um, blue is predicted inhibition of specific nodes or molecules, right? And the lines as well will be different colors. So if you increase the measurements of, for example, morphine, right? If the relationship leads to an activation, right? That line will turn a orange color like this. If what's it called? After increasing the measurements of a molecule such as morphine, the line that's connecting it to another node turns blue like this, right? That means that, like, because of increasing the measurements of morphine, that specific relationship will lead to an inhibition. If it's a yellow color like this, that means that the findings are inconsistent with the state of the downstream molecule. And if it's just gray, that means that there's no predicted effect. So using the ingenuity data, the publications that IPA has accumulated together, the software is not able to make a prediction of whether or not there will be activation or inhibition, right? So that's basically what the symbols are. We'll also be looking at some examples, right? So you'll have a better sense of how it looks. So the examples that we'll be looking at rather, are ethanol connected to TFEB, and we'll specifically looking at macrophages. We'll be also looking at morphine connected to TFEB. This will also be specifically in macrophages. And then we'll be looking at ethanol plus morphine connected to TFEB. So separately, how ethanol to TFEB looks, separately, how morphine to TFEB looks in macrophages, and how ethanol plus morphine look when connected to TFEB. And again, this is also in macrophages. So we'll start with our first example with ethanol connected to TFEB, how it would look after we use the molecule activity predictor. Okay. So we have ethanol over here. So we go ahead and search for ethanol on our search bar. We can either click enter on our computer to get all the related search options to ethanol, or if ethanol appears down here, we can just click for ethanol as well. But in this case, we've just gone ahead and clicked enter on our computer. So we get all the related search options to ethanol. We'll select the first option right here, ethanol. We'll add it to our pathway. We'll add it as a symbol, and then we'll click OK. And then we get ethanol on our pathway over here. Then we can go ahead and also add TFEB. If TFEB appears here, we can also just click TFEB here, or we can just click enter on our computer, and that will show us the related search options to TFEB. So we clicked enter on our computer. We can select for TFEB over here, the first option, add it to our pathway, and we'll add it to new my pathway one, which is the pathway that we have open right here. Okay, so we click on new my pathway one, and TFEB gets added, right? Then we'll go on to Path Explorer. So we're going to be comparing, ethanol connected to TFEB. So in order to do that, we have to use the Path Explorer function. So we go on Build, we select a tool, we click on Path Explorer. That takes us to this page here, right? And we can, set ethanol or TFEB as either set A or set B. We can set either or as set A or set B, but we'll just set ethanol as set A. So we click on ethanol. We select for ethanol. Once ethanol is selected for, it gets a blue sort of highlight like this. It gets a blue color. That's how we know that it's been selected for. So we select for ethanol. We add it as set A. And then we also set our direction going from ethanol to TFEB. So in this case, ethanol is set A and TFEB will be set B. So going from set A to set B, okay? We'll then also add TFEB to set B. So we click on TFEB. TFEB gets selected for. Once it gets selected for, it gets a blue shade. We click add. So TFEB is added to set B. We can then filter for macrophages. So we go down to our filter options in tissues and cell lines. We'll select for macrophages. All right. Then we can go ahead and apply those changes. All right. And we find that there is just one relationship between ethanol to TFEB. We can click here to add that pathway, to select for the pathway that we want to add. And we'll click add to my pathway. And it gets added like this. We can then just go ahead and rearrange it to make it look a little bit more visual. Then we'll move around the different nodes to make it a little bit more linear like this. Okay. Then in order to find molecule activity predictor, we have to click this overlay button right here. Okay. So we click on overlay, we click on select a tool, and then we can find molecule activity predictor, which is also called MAP short form. So we can click molecule activity predictor right here. Okay. So we click on molecule at map over here. Upon clicking map, we get this page over here. Okay, so we can see that there's a predicted activation. There's like the different. Basically, this is allowing you to increase or decrease measurements. So the red icon over here allows you to increase the measurements of a certain node. The green icon over here allows you to decrease the measurements of a certain node. Okay, so we'll start off, and this over here as well basically allows you to select the direction. So whether or not you want to see the downstream effects after you increase the measurements or decrease the measurements, if you want to see the upstream effects, or you want to see the upstream and downstream at the same time. So you're able to select for if you want upstream, downstream, or upstream and downstream at the same time. In this case, we'll be selecting for downstream only because we want to see the effects that ethanol has on TFEB. Okay, after we increase or decrease ethanol. So we'll select for downstream, right? And then we'll select for the increased measurements. So for increased measurements, it's this red button right here, right? So you'll see it has a red little line at the bottom. If you click this, this will basically select for increased measurements, right? So you click this button, and upon clicking that button, once you use molecule activity predictor, you'll see that your cursor will turn into sort of a paint icon, right? So that denotes that, okay, if you click on a node, that node will then increase in measurement, right? So we click on this, you'll see that your cursor will change into sort of a paint icon. then you can go ahead and click on the molecule or node that you want to increase in measurement. In this case, we want to increase the measurement of ethanol. So we click on ethanol and it turns a red color like this, right? And basically, this icon over here, it tells us if there is predicted activation on or not. So you just want to also make sure before you, come to any, sometimes, a predicted activation might be off. So just make sure that predicted activation is on. The predicted activation in this case is on. However, ethanol does not seem to have any predicted activation or inhibition of the downstream molecules, right? So that's the effect that we see. There is no predicted activation or inhibition of TFEB or any of the downstream molecules, right? We can also then check for decreased measurements. Decreased measurements is this green one right here. So we click on this. Then we can take our cursor. You'll see that your cursor turns into sort of this paint icon. You can click on ethanol over here. It turns a green color like this. And just make sure that predicted activation is on, which it is. And we can see that there is no predicted activation or inhibition of any of the downstream molecules. So in this case, there is none. There is no predicted activation or inhibition. However, what we'll do is that we'll also add the shortest paths plus one. So this is another utilization, is that if you don't see any sort of prediction with shortest paths, you can also just add shortest paths plus one to see if there's any predicted activity, right? So what we do is that we go to our build feature again. We click on Path Explorer right here, okay? Then we can go over here. We'll be taken to this page, right? And we can click on shortest paths. We can select for shortest paths plus one. We can see that there's a total of 3 relationships in shortest paths plus one. All right. We can select for that. That shows us the different relationships that are in the shortest paths plus one. We can click here to select for all of them. We can then add them to our pathway. And we see that after adding shortest path plus one, there is in fact a predicted activity. So we see that after adding shortest path plus one, TFEB has a slight predicted activation. So again, the color denotes the level of predicted activation or inhibition. So in this case, because it is a lighter shade of orange, it means that there is there's less confidence using the publication data in its activation. So there is some activation, right? But it's not such strong. It's not a strong prediction based off of the publication data, basically, right? So we have that. We can also then check for the decreased measurements to see what effect that has. If you decrease the measurements of ethanol, including the shortest path plus one, what effect that will have on TFEB, right? So we can go ahead and add that as well to see if we decrease measurements, what effect that will have on TFEB. So we click here, we click on ethanol. Ethanol turns a green color like this. And you can see that after decreasing the measurements of ethanol, and also including shortest path plus one, TFEB has decreased measurements. So, shortest paths, there was no predicted activity. But after adding what's called shortest path plus one, we see that increased measurements of ethanol result in predicted activation of TFEB, and decreased measurements of ethanol result in predicted inhibition of TFEB, right? So increased measurements result in predicted activation, decreased measurements result in predicted inhibition. Okay, so that's sort of what we see, the relationship that we see here. Okay, now we can also check for morphine. So I've included TFEB in our pathway here. I didn't remove it from our pathway. I'll add morphine to our pathway. So we can type for morphine here. If morphine appears on our search thread over here, we can just select for morphine. In this case, I'm just going to click enter on our computer and get the related search threads to morphine. We'll select the first option here. We'll add it to our pathway. We'll add it as a symbol. We'll click OK. Now we have both morphine and TFEB on our pathway. We'll then use Path Explorer to connect morphine to TFEB. So to do that, we go to the build feature right here. We'll select a tool. We'll go to Path Explorer. Okay. In Path Explorer, we'll then add morphine to set A. So we click on morphine. Morphine will then get a circular, what's it called? A blue highlight like this. That's how we know that morphine has been selected for. I've already gone ahead and added morphine and TFEB already to set A and set B. So I clicked on morphine. It turned blue, added to set A. I clicked on TFEB. It turned blue like this. then I added to set B, and I made sure that the direction was going from set A to set B. And in set A, there is morphine, set B, there is TFEB, okay? Then I'll also select for macrophages specifically because that's what we're looking at. We're looking at morphine to TFEB in macrophages, ethanol to TFEB in macrophages. So just to keep that consistent, right? We'll select for macrophages, we'll apply those changes, right? And we'll see that there is one relationship that we find in the shortest paths that connects morphine to TFEB, okay? We'll select here to click on all the relationships, and we'll add that to our pathway. Right, we get this added to our pathway here. We can then go on to molecule activity predictor. So to get to molecule activity predictor, we click on overlay, which is right beside the build function. So right beside the build function, there's overlay, click on that. We click select a tool. We click on molecule activity predictor, which is map, right? We click on that. That takes us to this page right here. We'll make sure that our predicted effects are going downstream to see like the downstream molecules of morphine in this pathway. We want to see that prediction, right? We'll check first for increased measurements. The increased measurements is this icon right here. We click on this with our cursor, right? And then upon clicking this, we can then click on morphine right here. And we see that morphine turns a red color like this. And we can see that after we increase the measurements of morphine, that there is a predicted inhibition of TFEB. So if you remember ethanol, after we increase the measurements in shortest path +1, there was a predicted activation. With morphine, after we increase the measurements, there is a predicted inhibition. So it is the opposite effect, right? So just to remind you. So ethanol, we increase the measurements, there was predicted activation. Morphine, however, after we increase the measurements, there's predicted inhibition. So it's the opposite effect here, right? We'll then also check for decreased measurements. So we'll click on this. Again, our cursor will turn into sort of a paint icon. We can then click on morphine over here. Morphine will turn green like this. That shows us that morphine has been decreased in measurements, right? We click on that, and then we can see that after decreasing the measurements of morphine, we see that TFEB has predicted what's called predicted activation. So it is, again, the opposite of what we would expect with ethanol, right? So ethanol, after we decrease the measurements right here, we saw that TFEB had decreased measurements. It turned blue like this, right? But for morphine, after we decrease the measurements, we saw that there was activation. So again, the opposite effect of ethanol. And again, like a lot like ethanol as well, they're like where the shade is a little bit lighter, right? The same can be said for morphine as well. It might be a little bit darker, but again, there's not a strong, basically, uh, there's not a strong prediction of activation, right? It is a lesser prediction based off the publication data that they have. So it's not a strong relationship that shows that there's predicted inhibition or activation, right? If it's a darker shade, that would mean that there's a stronger prediction. The lighter shades mean that there's a less strong prediction, okay? So because we also included the shortest path +1 with ethanol and TFEB, we'll also do the same with morphine, okay? So we'll add the shortest paths +1 over here. So we'll click on shortest paths. We'll add shortest paths +1. We see that there is only one relationship rather. So we'll click on shortest paths +1. We'll then click on here to add the relationship in shortest paths +1. We'll then add it to our pathway. And upon adding it to our pathway, we see that it's added over here. There's no real significant effect on the predicted inhibition of TFEB. So this is shortest paths. It's this shade of blue. After adding shortest paths +1, there's not a significant change, if any change at all. So we can do the same then for decreased measurements of morphine to see how that looks after adding the shortest paths +1. So after selecting for decreased measurements, right, we click on morphine, it turns a green color like this. We see that it is also, around a similar shade of orange. So we see here, this is shortest paths. It's this shade of orange. It's around the same, if any difference at all, okay? So that's what we see overall. So the overall effect is that if we increase the measurements of ethanol, there's activation of TFEB. With morphine, if you increase the measurements, there's decreased activation. There's inhibition. So, their effects are sort of the opposite over here, right? That's what we see. So now what we're going to do is that we're going to see, okay, if we have both morphine and ethanol, right? Because their effects are sort of the opposite of one another, right? If in a pathway we had both morphine and ethanol at the same time, what effect would that have on TFEB? Would TFEB be activated? Would TFEB be inhibited, right? So we're able to do something like this, right? So we'll go ahead and simulate this, right? See what actually happens to TFEB. Does it get activated, inhibited? We'll check that right now. So what we do is that we will use the path explorer function to connect morphine and ethanol, right, to TFEB. So we'll select for morphine and ethanol. We'll add that as set A, right? We'll also click on TFEB right here. We'll add that to set B. And we're making sure that our direction is set from set A, and set A being ethanol and morphine, to set B being TFEB, right? So we make sure that our direction is set from set A to set B. And then we'll also select for macrophages as well, because that is our specification for our other relationships as well, or our other pathways rather as well. So we select for macrophages, we click apply, okay? And we see that in the shortest paths, there are two relationships right here, right? So we'll click on here to select for all the relationships. We'll add that to our pathway. And it looks something like this. And what we'll go ahead and do, in fact, is that we'll also add the shortest paths plus one from now, because if you remember, ethanol over here had no predicted activity in just the shortest paths, right? So it's sort of redundant to actually add, just to see what will happen in shortest paths plus one with morphine and ethanol, because we already know that in the shortest paths, ethanol has no activity. So it'll just be the activity of morphine that's going to show, right? So we'll go ahead and just add the shortest paths plus one from now, because we know that ethanol does have some activity in the shortest paths plus one, but it has no activity with the shortest paths. So we'll add the shortest paths plus one. We see that there's 4 relationships here. We'll click on that. We'll click here to add all the relationships. We'll add that to our pathway. All right, so it gets added to our pathway here, right? I've already gone ahead and rearranged the pathway to make it a little bit more visually appealing, right? To make it a little bit more congruent. Then we'll go to molecule activity predictor. As mentioned before, to get to molecule activity predictor, we click on the overlay button, which is right beside build. We click on overlay. We then click select a tool. We can then select for molecule activity predictor. We go ahead and do that. We'll then select for the downstream predictions. We'll make sure that our predictions are on as well, right? And then right now we'll be selecting for increased measurements. So we'll be increasing the measurements of both morphine and ethanol, seeing if both of their measurements are increased at the same time, what effect that has on activation or predicted activation or inhibition of TFEB. So we'll go ahead and do that. We selected for increased measurements. We took our cursor, we clicked on morphine. Morphine turned red, ethanol turned red, and we can see that after doing that, TFEB has a predicted inhibition. So both of them combined together, we can see that if ethanol and morphine both were increased in measurements, there'd be predicted inhibition of TFEB. That is the overall effect, right? Now we can do the same thing with decreased measurements. So if you were to click on this icon, right, this icon, we click on this, our cursor changes sort of into a paint icon. We click on morphine, morphine turns green. We click on ethanol, ethanol turns green. So both of them are decreased in measurement. We can see that after decreasing the measurement, we see that TFEB has a predicted activation. So both of them combined are both of them, both morphine and ethanol combined, and we decrease the measurements of both, we see that there's a predicted activation, and both of them increase in measurements, we see that there's a predicted inhibition. So that's the combined effect of both, right? The combined effects more so reflects what the effects of morphine are. So that's what you're able to do. You're also able to say, for example, in a pathway, you could have also increased the measurements of morphine and decrease the measurements of ethanol, right? You're also able to do something like that. You can add multiple different molecules. You're not just limited to 2, right? You're not just limited to morphine, ethanol, right? You can add like 3, 4 molecules as well. increase some, decrease some, and see the effect that it has downstream. So you can really just sort of play around with it, right? See, like, okay, using the Ingenuity data, what predicted effects, what predicted activities there's going to be, right? So that's the molecule activity predictor. I hope you got an understanding of that. Now we're also going to be discussing the trim function as well. Okay. So the trim function basically is so basically utilize the trim function after you've already created your pathway. Okay. So say you've used the grow function to grow a molecule such as morphine as an example, right? Or you've used the path explore function to connect two molecules together. So for example, like morphine to TFEB together, right? You've already connected the pathways, right? But you want to then remove certain relationships, right? To remove those relationships from your pathway, you can use the trim function for it, right? So if you remember from our filter options, right, we have our data sources, mRNA confidence level, species, right? You can then use these filter options to remove certain relationships based off our criteria. So for example, if you want to remove relationships, that are or nodes that are, for example, um, that are not human studies, right? So you want to remove animal studies. So you want to remove studies in rats. You want to remove studies in mice, right? So you can go ahead and click species, right, in the trim function, and you can remove those specific relationships with the trim function. So it will only show you really what's it called relationships that are in humans, right? So it'll remove the what's it called animal studies as an example, right? Or say for example, you want to see older studies as an example, right? So you can use the trim function to select for the newer studies, right? So for example, studies within the last year, last 10 years, right? You can go ahead and select that in the publication date range, and you can remove those specific studies in the last 10 years, and it'll only show you the older studies, right? So you can trim out the newer studies. So trim function is that you can remove relationships that you don't want in your pathway. So we'll use an example with morphine here, right, to see how that might look. So I have morphine on our pathway right here. Morphine is right here. I've already gone ahead and used the grow feature to grow morphine. I have not filtered it at all. So it's including all of the different, all the different data sources, species, tissues, and cell lines. All of that is included in our pathway right here. And we can see that there are 307 nodes and 307 relationships that were added. Okay. So using the grow feature, no filtering at all, there's 307 nodes. The nodes being these specific data or specific points on our pathway. So, this the triangles, the specific triangles that we might see on our pathway, the diamond shapes, right? They denote different things. For example, like a chemical would be an oval shape, right? Cytokine would be a square shape, right? So we see that there are 307 different nodes and there are 307 relationships that were added. The relationships being the individual lines that are connecting morphine to the different nodes. The relationships are the lines, the nodes are these individual points right here, okay? So what we'll do then was that we want to trim some of this, right? So you want to remove some of the relationships. In order to get to the trim function, we click on build right here. We select a tool, we go to the trim function, right? Once we click on the trim function, it will take us to the same filter page right here. So we're able to, then select, okay, what do we want to remove from our pathway? What specific things do we not want to keep? So as an example, right, say for example, we don't want to include the Ingenuity expert information. So IPA's own Ingenuity data, we only want third-party information, right? So we click on here to remove the Ingenuity data, right? And say, for example, we don't want human studies. We only want animal studies, right? So we can click on here to remove human studies, right? And then we'll go ahead and apply those changes. So we see that our pathway, which started like this, becomes something sort of like this, right? So we see here that 265 nodes and 265 relations were removed. So based off our specifications, we didn't want IPA's own Ingenuity data, and we didn't want human studies, right? Once we applied those changes, we're only left with these specific relationships. 265 nodes were removed, these individual points right here, and 265 relationships were also removed. So these lines are here, right? So we have the trim function like this, right? Trim function removes. Alternatively, we have the keep function. The keep function is okay, so we only keep the relationships that we want. Everything else will be removed. So say for example, like we only want human studies, right? We don't want any animal studies, right? So with the key function, you can select for which ones you want to keep in your pathway and which ones will then get removed, right? So it's sort of the opposite of the trim function. We'll use the same example with morphine to see how that might look. Okay, so we'll be using morphine. So I've already added to our pathway. I use the grow function to get morphine. We can see that there are 307 nodes and 307 relationships that were added. Okay, we'll then go to the build function. So both the trim and the key function are both in the build section right here, right? As is the grow and the path explore. The only one that isn't in build is the molecule activity predictor, which is an overlay, right? All the other ones are in grow, or sorry, are in build. So we'll click on keep right here. We click on keep. We get taken to our different filter options, right? The filter options basically look like this, right? You have seen this before, right? So the different filter options that we can use to like keep the specific relationships that we want. So in this case, you want to keep the Ingenuity data. So we only want the relationships, like the relationships and the nodes that are from the Ingenuity data, IPA's own publication data that they've accumulated. And we only want to keep human studies as well, right? We don't want mouse studies, we don't want rat studies, right? So we can go ahead and apply those changes right here. Once applying those changes, we see that, okay, it looks something like this, right? We can see that there are 265 nodes and 0 relationships kept. So, this might be confusing, right? But I'll sort of explain this. So what this basically means is that, okay, after we selected for IPA's own Ingenuity data and we selected for human studies, these nodes were related. So these nodes were found in human studies and IPA's own Ingenuity data, but they had no relationship to morphine though, with our specifications, right? So if you selected for animal studies and third-party sources, you might have found a relationship with morphine, right? But with these specific, like with just IPA's own Ingenuity data and human studies, there is no relationship with morphine that is found. Okay, so that's what that basically means, right? And you're able to, like basically utilize this. If you want to like certain, after you've already created a relationship, if you want to remove a certain you want to like basically specify your data further, right? You're able to do that with the keep function or the trim function as well. So trim function is you remove certain relationships. Keep function is you only keep the relationships that you've selected for, right? That's the basic difference between the two. And yeah, we'll take any questions right now if anyone has any questions.
So my question is that when we were using when we're seeing the morphine and TFAB relation, we saw that when we were increasing the measurements, when we were increasing the measurements of morphine, then we were seeing that there is a result in the second node, that is activation or inhibition. But when we were just doing the opposite, when we were uh, decreasing the measurement, then we also saw the result as an opposite, like the act if earlier it was activation, then the next it was inhibition. So is it compulsory? Is it compulsory?
No. That's not compulsory. So if you increase the measurements, there you might have a scenario where it is also activated. But if you decrease the measurements, you might have a scenario where it's also activated as well. So I have come across certain situations where in both cases it is activated as well. So it's not necessary that it'll be the opposite. It can also be both activated as well. Like just from my personal experience, I've come across that.
Thank you, sir.
The trim function affect the overall data of the research? Yes, it can affect the overall data because again, you are basically you're filtering the data, right? So you're including certain relationships and you're excluding certain relationships. So the effect that you might see after using molecular activity predictor because you've included certain relationships and excluded others, it might show that okay, one molecule before trimming it was activated, and after trimming that molecule is now inhibited. So yes, it can also affect the results of the data as well. So I guess we could then move on to the quiz then. If anyone does have any questions, you can let me know. We'll be moving on to the quiz. So I'll share the quiz code with you right now. Okay. So this is the QR code for the quiz. You can just use your phones to scan the QR code, and it will take you then to a page that looks like this. You can then enter the game pin in. I will be sharing the game pin with you momentarily, but you can just scan the QR code right now on your phones. All right, so I will be sharing the game pin with you right now. Okay, so I'll just add the game pin to the chat as well. So I believe you can also just directly go onto the game as well with the game pin. So that's included in the chat right there. Okay. So we'll give until around let's say 12:06 for everyone to join. So we'll begin around 12:06. If anyone needs more time, you can let me know. Like we'll give around 2 more minutes additional if anyone needs more time on top of that. So we'll begin around 12:06. Okay, has everyone been able to join? If everyone has been able to join, we can just begin right now. Does anyone need more additional time to join, or I can just begin now then? Okay.
सुना सब रखा था
Okay, so we'll begin the quiz now. I hope everyone was able to join. All right, we're going to be starting the quiz now.
हो भी जाए यार टाइम sama itu sama sama hujannya sama dan sama dan
Right. Okay, so the results from today's quiz and all the previous quizzes as well will be tallied. I will be including the results from the different quizzes, however many points everyone has received on the Google Doc. So that information will be available to you. So I will be adding it to the Google Doc. Okay, so the Google document right here. I will include a document that shows however many points everyone has received prior to going into the final session, so including this session as well. And in our final session, we'll just discuss however many points everyone has received. Just one other thing before we end today's session, the task for the next session. So I want you to use the Path Explorer feature to connect midazolam and ethanol to GABA, and also include the shortest paths +1 in your pathway, including the shortest paths. So shortest paths plus shortest paths +1 in your pathway, and then use molecule activity predictor to increase the measurements for both midazolam and ethanol, then to decrease the measurements of both midazolam and ethanol, and see what impact it has on GABA. So whether it leads to activation or inhibition of GABA. So I want you to do that for the next session. Just another pointer that if you would have activated your trial at around the second session, it should be expiring sometime early next week. So if you're able to do the task for the next session, you should try to do it by this weekend, preferably because the trial would be expiring around early next week. It's only a 2-week trial, unfortunately, so it would be expiring around early next week. So yeah, if anyone else has any further questions, we can address any further questions anyone may have. Otherwise, this would be the end of our session. So if anyone has any further questions, more than welcome to ask anything. I'll conclude our session for today then, if no one has questions. I hope to see all of you for our final session, which will be held on the 31st of August. A reminder again that our final session will be a review session, and it will also include the final quiz as well, where there is a monetary prize for coming first, second, third, fourth, fifth. I will also include a Google Doc, highlighting however many points who has received for the previous sessions. So that will be included in the Google Doc. So you can see however many points you have. That will be included into the tally for the final quiz. So I hope to see all of you then for the final session on the 31st.